Electrical potential. So before we start talking about electrical potential, let's go back to electrical potential energy. So a charge Q at origin 0, another charge Q naught is moved from RA to RB. Then the change in potential energy will be given by 1 over 4 pi epsilon naught Q1, Q2, 1 over RA minus 1 over RB. So for a test charge, which is 2 times Q naught, the electrical potential energy will be 2 times delta U naught. For a test charge that is 3 times Q naught, that has a charge 3 times Q naught, and the change in potential energy will be 3 times delta U. So potential energy is directly proportional to the size of the test charge. As the test charge increases, the electrical potential energy increases. But what if you wanted to calculate a term that is independent of the test charge? What would you have to do? Well, what you will have to do is you will have to get rid of the Q naught, which is the test charge, right? That term is now going to be called electrical potential difference, or delta V. So delta V, by definition, is the change in electrical potential energy divided by the test charge. Okay? The units are called 1 volt, which is joules per coulomb. Just like potential energy, electrical potential is a scalar quantity. So if you were to compare the two side by side, you would see electrical potential energy is 1 over 4 pi epsilon naught Q naught over R, whereas electrical potential difference is 1 over 4 pi epsilon naught Q over R. So electrical potential difference does not depend on the test charge. Or U equals Q naught V. So electrical potential energy and electrical potential are related with the test charge. So in words, you can define it as potential is equals to potential energy per unit of charge. Or delta V equals delta U over Q. Remember, potential difference is not the same as potential energy. So now let's come up with a definition of potential difference. So potential difference between points A and B is defined as the change in potential energy, final minus initial, of a charge Q moved from point A to B divided by the size of the charge. So electrical potential energy is delta V equals change in potential energy divided by Q. Another way of defining it is delta V equals delta U over Q naught, which is equals to F dot dl, or divided by Q naught, or F dl over Q naught, or E dl. And we will talk about this in a little bit. Another factor that's very important that I want to talk about, if you have an isolated positive charge, the potential around it is going to be positive. Now what does that mean? So for a positive charge, that means to move a positive test charge from infinity to somewhere close to this positive charge, you will have to do negative work, which means you will have positive change in potential and potential energy, which means you will have positive change in potential. Okay? If you have a negative, isolated negative charge, moving a test charge from infinity to close to it will require positive work, which will imply that there will be negative potential energy and in fact negative potential. Okay? So the electric force in this case that is done on the charge will be positive. On the other hand, if a potential is 0 at a point, no net work is done by the electrical force as the test charge moves from infinity to that point. So here's the thing that's important to remember. Even though as you bring a charge from infinity to that point, it might move through regions where it experiences attractive or repulsive electrical forces, it only matters what happens where it ends and where it started from. Nothing in the middle. So the potential of a point at 0 does not necessarily mean electrical field at that point is 0. Okay? So we talked about an electron volt. Electron volt is the energy acquired by the particle of charge E when it moves through a potential difference of 1 volt. So 1 electron volt is actually equals to 1.6 times 10 to the minus 9 coulomb times 1 volt, or 1.6 times 10 to the 19 joules. So this is a very, very, very tiny amount of energy on a macroscopic world, like our world, but electrons and atoms have typically very few electron volts of energy, and it becomes really, really important when you go really, really tiny. Now, how do you get potential from field? Well, we talked about this a little bit ago, and here's a definition. If we move a test charge Q0 from some initial point to some final point in an electric field, then change in potential will equals minus Q E dot dl. Or, if you take this Q over to this side, it will become U over Q minus U over Q. So delta potential final minus potential initial equals minus integral from I to F E dot dl, or delta V, which is the change in potential, equals minus E dot dl. So, in a nutshell, what do you need to remember about electrical potential? You need to remember, first off, electrical potential and electrical potential energy are not the same thing. They are related, but they are not the same thing. They are related by Q naught, which is the test charge. So electrical potential difference is the work per unit charge that must be done to move a charge from one point to another without changing its kinetic energy. Another thing to remember about, it is always necessary to define where both U and V, potential energy, and potential are zero. Here we define V to be zero at infinite distance from the sources of the electrical field, which is a very, very good idea. However, sometimes it might be convenient to define V to be zero at Earth. For example, when you're grounding it, right? And so be very careful when you read these questions. It should be clear from the context where V is defined to be zero.